Hello everybody, my name is Bhatt and today I will talk about a few strategies that I feel that can be used to solve the Goldbach conjecture. Now this is coming from an extremely beginner's point of view because I am still an undergrad and there are a lot of things that I should learn about which are extremely essential for tackling these unsolved problems. However, from what I know, I feel that there are 6 different strategies that could be used to approach this problem. Now I don't know if any of these 6 will ever work or if the final proof that somebody someday comes up with will have anything to do with any of this, or maybe more than one of this will work out. I don't know, but this is just my idea. So here I have written these 6 strategies and now I will explain them one by one, and I will not take up too much time into explaining what should actually be done, but I'll just present the idea. So the first strategy that could be used is modularity, sieves, inclusion and exclusion. So that's one of the most famous techniques in these kind of problems. So what you do is you do the process of sieving. You look at different modular classes and you do some inclusion, exclusion. You say that there should not be overlapping, so you reduce some numbers, you add some numbers. It's more like the sieve of Eratosthenes, you see. So that is one strategy that could be used for the Goldbach conjecture, although there are a lot more useful sieves for this particular problem, like the Bruns sieve or the Lagrange sieve or whatever that is, and you could treat this as a sieve problem, but this, according to me, this would be the least likely of all the 6 strategies, because this is something that many analytical number theorists all over the world are currently working on. So I feel if this was something that could work, then by now somebody would have a solution. Although I would not rule it out completely, because I feel ultimately the Goldbach conjecture talks about even numbers and prime numbers, right? So that's nothing but modularities and how multiples of numbers behave and where there are primes and composite distribution of primes. So I think the final proof would have something to do with this, but we don't know if this will be the entire part of the proof. The second strategy, which I recently felt could be used, is a Cartesian plane with only primes. So what is that? So let me show you what I mean by that. Let me actually erase the other things and I will write them again later when I talk about them. So a Cartesian plane with primes, what I'm trying to say here is, let's create a hypothetical graph and let us say that we only have prime numbers along the x-axis and prime numbers along the y-axis, and I don't really need to space them out evenly. I just say that the first unit is the first prime, the second unit is the second prime, and so on. We don't care about the gaps, and I'm going to start with the number 3 because all the Goldbach solutions greater than 4 will only include primes greater than 3. So if we plot the primes like this, 3, 5, 7, 11, 13, 17, remember, I'm not spacing them out evenly, and I don't think they should be, because we don't really care what they are. We are just saying that the primes are being plotted evenly, and we do the same thing on the y-axis and so on. And I say that a point on this plane is defined as a sum of the 2 primes of its axis. For example, if there is a dot over here, the coordinates are 5, 5, so then it would represent the even number 10 because it is 5 plus 5. Or if there's a point over here, this would be 20 because it's 7, 13. So it's a different sort of a graph. It doesn't follow the same rules of the current x-axis, y-axis that we know of. This is a different thing that I thought of very recently, and I think, so what we could try to prove here is that we say that we plot all the even numbers on this graph. So we plot all the points actually. For 3 I plot points all the way to infinity. For 5 I plot all the way to infinity, and I do that for every prime. And then you somehow show that every even number is somehow going to be on this graph, because that's what the Goldbach conjecture says. You want every even number to be part of this graph somewhere or the other. Or you say that it is not possible that an even number can exist outside of this graph, because if it's an even number, you say that it has to exist somewhere on the graph. So if you can prove that, you prove the Goldbach conjecture. So this is a new strategy. Different strategies look at it. The second strategy. The third strategy is using probability and the prime number theorem. Now this is also something that all great mathematicians have tried, and I would again say that this is, if this was the strategy that could solve the conjecture, maybe people would have done it now. But again, as I said,
I don't think any of these foundational strategies can be ruled out. They would always have a part to play. It is just as to how much of a part they will play. So let us say that
if we were to attempt the Goldbach conjecture using probability and the prime number theorem, we would try to prove or show in some sense that as the even number approaches infinity, as the even number becomes extremely large, using the prime number theorem, you say that there are so many prime numbers that are smaller than it, and what is the chance that at least two of them can be used to add up to form that even number. So in a more explicit sense, what I'm trying to say is, if an even number is existing, if this is my even number, I actually spoke about this in some of my previous videos. So this is my even number. I say that this is extremely large, and this is the half of the even number, and we have some primes present over here, and we have some primes present over here. There will be more primes on this side, because the prime density gets lesser and lesser as the number gets larger. So you try to show that there is no way that all of them are located at different points. It has to be at least one pair that is equidistant from the midpoint of the even number. So then the two of them can be used to add up to form that even number. So there you are using probability. You say that the probability that a number is prime is 1 over log x, and then you know the number of primes that are present using the prime number theorem, and then you manipulate it in some way to show that if the even number becomes extremely large, it has to be a sum of two primes, because probability makes it almost zero that it cannot be a sum of two primes. So this is a pseudo proof that I gave you, but I'm pretty sure it would involve a lot of other advanced techniques, but that is one way to look at it. The fourth method that I feel could be used is something very, very elementary and used in all basic math courses. It's called proving by contradiction, and actually that is how Fermat's last theorem was proved. I mean, it's not the only thing that was used in Fermat's last theorem, but that was the first statement in the proof. Andrew Weil said that we will assume that a to the power n plus b to the power n equals c to the power n has a solution for n greater than 2, and then he does everything over hundreds of pages, and then he says that it's not possible. So if we were to prove the Goldbach conjecture using contradiction, my strategy would be, we try to create an even number which cannot be represented as a sum of two primes, and then we fail, and then we say that every even number has to be a sum of two primes. I mean, this is a very broad idea. How do you even create such an even number? All of that is something I do not know at this point, but I'm saying we set off on a journey and we say that, okay, is there a way by which I can create an even number that will not be a sum of two primes? And then I say that such an even number cannot be created, thus every even number has to be a sum of two primes. So trying to prove by contradiction. The fifth strategy is something extremely powerful if it can be implemented, not only for the Goldbach conjecture, but this strategy can be used to solve almost any conjecture in the world. And what I feel is, suppose, now see, there are a lot of patterns going on in numbers which we are unaware of, but suppose somebody says that, okay, we don't know what these patterns are, but if they hold true all the way up to some large number, whether it is 10 to the power 10 or 10 to the power 20 or 10 to the power 50 or whatever that is, somebody says that if numbers behave in a certain way up to a certain large number, then they will have to behave in that way forever. Suppose somebody can make such an observation, because I am very sure that there are very, very, very few conjectures that have not been tested up to this large number. And all the conjectures that have been tested up to 10 to the power 10 or 10 to the power 20, they still are, holding their, they're still true, whether it's the twin prime conjecture or the Goldbach conjecture, even the Riemann hypothesis for that matter, has been tested to 10 to the power 19, even the Collatz conjecture, and all these unsolved problems have been tested to a very large number. So can you generalize and say that although we do not know how prime numbers behave, although we do not know how numbers behave or how modularities behave, will they continue to behave like this forever if they behave like this up to a certain point? Because numbers are numbers ultimately, and they all have some pattern in them which we might know or might not know. So can you generalize and say that, well, if these many numbers are following the pattern, can you somehow say that it works for everything? These things are
kind of used in astronomy in a sense where you say that the universe might never collapse because all the laws and the laws of physics are working for so many years. You never say that the law of gravitation will change, right? Because you know that it has been working since 13.7 billion years, since when the Big Bang happened. So you kind of know that it will work forever. You know that V is equal to U plus AT will work forever. You know the Planck's constant will remain the same forever. Can you generalize something like that for mathematics and say that if all the numbers up to 10 to the power 20 can be represented as sum of two primes, they will always, all the numbers up to infinity can also be represented. That's fifth method. And the last method is using combinations, and this is something extremely interesting but extremely difficult to implement in reality, but I'll tell you how close it can actually lead us to the proof. So the strategy is this: you take an even number x and you list out all the prime numbers which are smaller than x. In fact, all of them. We say p1, p2, p3, all the way up to pn, which are all smaller than x, okay, smaller than x. And you try to see in how many ways they can all be combined together. So P1 can be added to P2, can be added to P3, P4, P5, all the way up to Pn. Then you take P2 and you say you can add it to P3, P4, P5. Then you see all these combinations, you list them out. And you see if the number of unique sums that can be generated out of those combinations will be same or larger or smaller than the number of even numbers smaller than x. You know for a fact that adding any two primes, I'm talking about primes greater than 3 by the way, adding any two primes should give an even number. So if you can somehow say how many unique sums there are, we need to be unique about it, because suppose my prime numbers are 3, 5, 7, 11, 13 and 17. 13 plus 7 is the same as 3 plus 17. So I need to find a way to only count the unique sums. So the unique sums here are 3 plus 5, 8, 3 plus 7, 10, 3 plus 11, 14, 3 plus 13, 16, 3 plus 17, 20. 5 plus 7, 12, 5 plus 11, 16 has already been counted, 5 plus 13, 18, 5 plus 17, 22. Let's not use that one, we'll only look at numbers that are smaller than 20. Let's say our x is 20 in this case. Next I do 7 plus 11, it has been counted, 7 plus 13 has been counted, 7 plus 17. So I have counted all these numbers. By the way, I can also do 3 plus 3 which is 6 and 5 plus 5 which is 10, and I think everything is done, right? So I listed the unique sums that can be generated using those prime numbers without counting anything twice, and now I have 1, 2, 3, 4, 5, 6, 7, 8 numbers. I have 8 numbers, and the number of even numbers that exist smaller than 20, which are greater than 4, is 8, which are 6, 8, 10, 12, 14, 16, 18, 20. This is a small case, so I can actually count these and look at it, but if you can generalize something for a larger even number, if this count will always be matching this combinations that you can do, then you can show that the number of solutions, the number of unique solutions are the same as the number of even numbers, which means every even number smaller than that x that we started with has to be represented as a sum of two primes which are smaller than x. So these are the 6 strategies I feel so far I have observed. Maybe over the next few months or few years I might come up with many other strategies, and what I would want to do at some point of time is combine these strategies and see if the pros of one strategy can make up for the cons of some other strategy, and together maybe combining bits and pieces of 6 different strategies, maybe we can come up with a proof. I don't know. So that's for the future. Thank you so much.